Hello everyone. In the last session, we have started unit number 8, that is satellite link design. In that session, we have seen basic transmission theory. Now, what do you mean by I'm going to revise it, a basic transmission theory that we have seen the ideal power received by an antenna. It depends on transmitting power, gain of receiving antenna, and the path loss. As transmitting power, we can also define it with the help of EIRP. That is a product of PT and GT. Okay, so we can say that the received power depends on EIRP, gain of receiving antenna, minus path loss. Why minus? Because we are always subtracting the loss, because as a power is going to be transmitted to the certain distance, our power is going to be attenuated. That's why it is going to be a decrease. That's why we are going to subtract the path loss from the actual transmitting power, as it is ideal. But we need to consider that the loss because of transmitting antenna, loss because of receiving antenna, and the distance between transmitting and the receiving antenna, right? In today's session, we will cover the system noise temperature and G by T ratio. G by T stands for gain temperature ratio, right? First of all, we are focusing on what do you mean by a noise temperature. Noise temperature that provides a way of determining how much thermal noise is going to be generated, whether it is because of active or the passive device in the receiving system. So at microwave frequency, a black body with physical temperature, that means a TP. TP stands for physical temperature and its unit is Kelvin, generated a electrical noise over a wide bandwidth, right? So what we are doing is we are simply determining how much thermal noise is going to be generated, because it shows its system noise temperature, right? So first we are considering the what do you mean by noise power. Pn. The basic equation for the noise power is K into Tn into B. Product of K, T and B. K stands for Boltzmann constant. Its value is 1.38 into 10 raised to minus 23. Unit is Joule per Kelvin, right? Also, we can convert this value into dB. How? We need to simply put 10 log base 10 1.38 into 10 raised to minus 23. On this, we can get the value in dB watt per kilo per hertz. Okay, we will get minus 228.6 for the value of K in dB. Why? Because every time we are going to calculate the received power in dB, so we are simply converting this value directly into dB. Or we can say that we can also simplify this expression, 10 log base 10 in bracket 1.38 as plus sign is there. So we are simply placing the plus sign and 10 log base 10 into 10 raised to minus 23. This is the simplest way to solve this term into dB. And if minus 23 is coming over here as it is in the exponent, that minus 23 into 10, that means minus 230. So whatever the answer will be there, we have to subtract it from minus 230. And we know that log base 10 is 1. This term is 1. This term will be 1 log 10 base 10, right? Now Tn is the noise temperature of source and B is its noise bandwidth, in which a noise power is measured in hertz. So the system noise temperature Ts is the noise temperature of the noise source at the input of noiseless receiver, which gives you the same noise power as the original receiver, right? Which is measured at the output of receiver, right? Now, how to calculate this system noise temperature? First, we are focusing on the diagram. You can see that plus sign is there. That means we are going to add temperature of noiseless RF amplifier, noiseless mixture, and noiseless IF amplifier, as these are 3-stage RF amplifier, mixture, and the IF amplifier, and we are considering this as a noiseless, right? So RF amplifier has a gain of G base RF, mixture has a gain having GM, and IF amplifier is GIF, gain of this. Okay. Now how to write the expression for this? Our input temperature is Tin and we are going to calculate its noise power. The basic equation is Pn is equal to K into Tn into B, right? We need to consider all the temperatures with gain factor. Starting from the last block, Pn is equal to GIF, that is a gain of IF amplifier, into K into T into Bn. But the T is for IF amplifier, that is TIF, right? Plus this block. So we need to again consider this GIF. As we are proceeding, we have to simply multiplying the gain of cascading stage. We know that if the amplifiers are connected in the cascading stage, the gain is going to be multiplied. Overall gain is going to be multiplied. For example, if the gain of amplifier 1 is G1, Gain of amplifier 2 is G2. Gain of amplifier 3 is G3. And all these three amplifiers are connected in the cascade form. So the overall gain G is equal to a product of G1, G2 and G3. G1 into G2 into G3. This is the gain of overall gain of cascading three amplifiers. As a G4 is connected, as amplifier 4 is connected, then we have to simply multiply this quantity with the G4. Okay. Now GIF into GM into KTB, and T temperature is for mixture, and B N, that is the noise bandwidth, right? Plus GIF plus GM plus GRF, GIM IF plus GM plus GRF into K into BN. But we need to add two temperatures, input temperatures and the RF temperature. RF amplifier's temperature. So T in plus TRF, right? So this is the noise power of a noiseless RF amplifier, mixture and the IF amplifier. So we are considering the noiseless component, and the system is also a noiseless. So how to calculate its noise temperature? So we have calculated its noise power. This is the expression which we have discussed earlier, in which the noisy device in the receiver are replaced by equivalent is its noiseless block with the same gain and its noise generated at the input. So total noise power at the output of IF amplifier of the receiver is Pn, that we have discussed based on this diagram. All right. So this equation can be written like GIF, we are simply make a common GIF, GM, GRF and KVN. We will get this expression like TRF plus TIN plus TM upon GRF plus TIF upon GRF GM. Okay. If we consider a single source, over here we have considered three sources. Now we are considering a single source of the noise. Then its noise temperature Ts will generate the same noise power Pn at its output. How? Because we are considering the noiseless receiver having the gain of GRF into GM into GIF. So GRF into GM into GIF into K multiplied with its system noise, that means a source of the noise Ts having a temperature, and multiply with its noise bandwidth. Okay, so this is the noise power of single source. Now we are simplifying the expression. Basic expression was KTN BN. We are going to equalize it with this expression, this one. Okay, so we will get the system noise temperature Ts, as K is going to be cancelled out, Bn is also going to be cancelled out. So the Ts, the system temperature, is input temperature plus temperature of RF amplifier plus temperature of mixture divided by gain of IF amplifier plus gain temperature of IF amplifier divided by gain of mixture and RF amplifier based on this diagram. If you are considering this parameter, then we have to write it like this: T in only T in plus TRF plus Tm upon GIF, Tm upon GIF and plus TIF upon GRF into GM. GRF for gain of RF amplifier and GM for gain of mixture. Okay. So this is the equation for a system noise temperature. And we know that what do you mean by noise figure? So it is the ratio of signal to noise power of input to the signal to noise ratio of output. So it defines the noise generated within the device. And if we are going to consider, it's a simple noise temperature, which is most useful in satellite communication. We are simply converting this noise figure to the noise temperature by T is equal to T0 in bracket noise figure minus 1. It is a linear ratio, so it is not in the decibel. Okay, if you want to represent it in the decibel, then we have to write it like noise factor. Okay, over here T0 is the reference temperature 290 degree Kelvin, right? This is the noise temperature. So here we have considered G by T ratio for the link equation, or you can say carrier by noise ratio. It's PT GT GR upon K TSBN into lambda upon 4 pi square, that is we have discussed earlier in the last session. We have simply just dividing with the Pn. This is for the carrier that we have discussed. PR receive power. This is the Pn. PR upon Pn, right? The PT GT upon KBN. GT GR upon TS is the gain of receiving antenna upon system temperature, lambda upon 4 pi R whole square. Okay, so this is the carrier by noise ratio. This is called G by T ratio for the earth station. So if you have any question, you can ask me at any time on my email ID. Till then, thank you for your attention.